Thanks, Sarah. Hello, everybody. My name is Niharika Nayak-Jingal, and I'm a program manager in the EPA CHP Partnership Program. Welcome to today's webinar, and we are really excited you could attend it. Just a brief background, the program's been around since 2001 and with a current roster of over 400 partners. The program focuses on removing technical, policy, and project development market barriers to CHP by engaging with the CHP industry, developing resources, and raising awareness on best practices in the CHP market. Today's webinar will leave you with an understanding of CHP and the different technologies that can be used to harness waste heat and produce heat and power. In the CHP lexicon, these technologies are often referred to as prime mover technologies. We will be covering primarily commercially available technologies for different types of CHP systems. There are waste heat to power systems as well, and this webinar's focus means some waste heat to power systems, also referred to as bottoming cycle CHP, will also be discussed. So this webinar, this site gives you an overview of the overall presentation. Chris Lyons from Solar Turbines will first give you an understanding of how combustion turbines can be used in a CHP unit. Mark Rouse from Capstone and Tony Leo from Fuel Cell Energy will do the same. From our experience, the choice of a technology is very site-specific, and project economics are based on current electricity prices being paid, fuel availability, and how much heat and power are needed. The three presentations will give you a rich understanding of these trade-offs. Ann Hampson from ICF will then provide an overview of the catalog of CHP technologies, which has been prepared with funding from US EPA and the Department of Energy. There will be an opportunity to respond to questions, some opportunity at the end of each presentation, and then right at the end where there will be the remaining questions answered in the Q&A session. So without any further ado, I'm going to turn this over to Chris. Chris?
Okay, thank you, Niharika. I appreciate the opportunity and the EPA CHP partnership allowing me to speak today. So for you that don't know me, I've been in the energy business for over 40 years. I started in the oil business. People call it oil and gas. Back then, gas was a waste product. Then I moved into heavy fuel oil, where we were injecting steam out in the San Joaquin Valley of California. And I worked in the coal business for a number of years until I was breathing in a lot of coal dust. I got into the natural gas business with Solar Turbines, and I've been here for about close to 20 years now. So you go to the next. So Solar Turbines, people wonder why we have the name Solar. We actually started in 1927 in San Diego as the Prudent Aircraft Company. And we built a few metal and aluminum aircraft, but then the recession came, and we slowly then changed our name to the Solar Aircraft Company. And our products were the Mars, the Jupiter, the Saturn, things like that. We have nothing to do with solar energy, but we've had the name since the 1930s, and we've had it for so long we didn't decide it was beneficial to us to change it. So what happened to us in the 1930s, we made exhaust manifolds, particularly for all the aircraft during World War II. We were probably one of the very large producer of those. We had plants in Iowa and in San Diego. We hired a number of women at that time. We probably had, of course, all the men were off fighting battles, but we were very capable of doing stainless steel fabrication. We actually developed the afterburner, and the development of the afterburner was really to help the military. They were losing more people to malaria, and this was a way to put out fog and things, heavy oils that would kill the mosquitoes, but they learned that it was a way to make more thrust. So that was some of the products we have. And then after World War II, we were deciding what we would do with all this manufacturing, so we got into rocket components, and then eventually got into gas turbines for portable fire pumps for the Navy. And then once they saw the success of that, they asked us to do it for Navy ship propulsion, and then in the early 60s we were making generator packages, and then now we're into natural gas compression. And a lot of this has been CHP over the years, and that's a big part of our power gen market is the combined heat and power. So if you could go to the next. So when we talk about combined heat and power, Obviously, just to make sure everybody's clear on that, 1 fuel in and then 2 outputs so that you get the maximum efficiency out of that source of energy. Today, some people, though, call it trigeneration because there could be even more than 2 uses. It could be 3, maybe in some cases 4, chilled water as an example. But I also bring up distributive generation. Distributive generation is typically a CHP plant is distributed, not a large central power plant. And the advantages of that is then to eliminate grid losses. During high peak demands, those losses can be up to as much as 9%. So when you look at what that costs in generation, that's quite a bit. So distributed generation can be localized, but it doesn't always have to be CHP. We do have some peaking plants as an example. So if you go to the next. So what's key for combined heat and power then is the thermal matching, so that you take the high-grade heat from a turbine, so you have a lot of energy needs in the back end, the thermal, steam as an example. We also make a recuperated gas turbine, the Mercury 50, that was partly developed by the Department of Energy, but it recovers some of that waste heat and puts it back in to improve efficiency in the combustion process for electrical generation. Examples of that, where I live in San Diego, Grossmont Hospital. We're in San Diego, we don't have a winter thermal heating load, so they don't have a big steam demand. And then if you get down into no heat demand, then a reciprocating engine that has a higher efficiency for generation might be a better choice. And being part of Caterpillar, we're part of the Energy and Transportation Group. We make all of these products, so we can kind of determine then which one of these products best fits the application. So key to it is the heat and power ratio is really, so if you go to the next. So what I'm going to focus on today is combustion turbine applications for combined heat and power. So a combustion turbine is really just a big, if you've been in the aerospace industry or aircraft, you know, you see a jet engine. Well, they're producing thrust to drive that aircraft into the sky. Well, we're taking that thrust, and instead of using it to fly an airplane, we're taking that energy and rotating the shaft to drive the generator to make the electric power. But because it's a volumetric machine, we still have a lot of mass flow. So our exhaust has about 15% oxygen in it. So it's a very high temperature, high grade heat. And with that high temperature exhaust and high oxygen content, you can vary the thermal by changing the thermal application. So in the wintertime, if you have a high thermal demand, steam demand, hot water demand, you can then increase it and have more efficiency because you're reducing the oxygen level. But typically these CHP applications with combustion turbines can then be anywhere from 70 as high as 90% lower heating value type efficiencies. So you can go to the next. So what type of industries use CHP? A whole vast variety. If you look at food processing as an example, customers of ours are people like that you well know, Sara Lee, General Mills, Coca-Cola, Frito-Lay. Pharmaceutical people, Biogen in Boston, Bristol Myers in Connecticut, Pfizer, Abbott Labs. If you look at pulp and paper, Kimberly-Clark is a big buyer of our combustion turbines for their applications. Georgia Pacific is another one. If you look at manufacturing, there are many, many companies. Examples are Sikorsky Aircraft, make helicopters. Hamilton Sundstrand, all United Technology companies. So those are just examples of manufacturing. If you go to the next. One of the others big is obviously in the oil industry, refining is obviously a big application because they're big steam demands. We have a number of refineries. Hospitals, the one in the upper right is actually the Mayo Clinic in Rochester, Minnesota. Universities, the bottom left picture is Caltech out in California. Utilities, we have a number of utilities. An example of a utility is Austin Energy at their Dell Hospital. I think that was an EPA Energy Star Award-winning plant. But they provide reliable power and steam and chilled water to that hospital. And they were able to get a platinum LEED certification for using CHP. If you go to the next. So hospitals are good examples because hospitals, in the case of the upper right applications, that's UMass Medical School in Worcester, Mass. That's a 7.5 megawatt cogen plant. They recover the heat by making steam. They have a steam turbine, a back pressure steam turbine, and then use the exhaust steam for heating in the wintertime and even air conditioning in the summertime. This plant, particularly the UMass, actually got from National Grid, the utility that serves them, a grant to help put in the cogen plant. The bottom picture is Montefiore Hospital in the Bronx, and that was installed in about 2000, the year 2000. But the interesting thing about this plant, if anybody recalls the 2003 August blackout in the Northeast when the entire Northeast was without power, this hospital remained in full services, operations, everything, because they had a cogen plant that was able to keep them isolated and operating with all of the chilling and electricity needed to do those services. And people were coming to that facility just for, to get out of the heat in August. And it's also a dual fuel unit, so if there's an interruption, you can do that. University examples. Cornell University was burning coal not many years ago, a few years back, and they decided to get off of coal and they put in a gas-fired 30 megawatt combined heat and power plant. The one below, the University of Connecticut, the interesting thing about that plant, that's a 20 megawatt plant, has 3 of our 7 megawatt turbines. It was actually financed by Caterpillar through a university lease financing program, which gave them low-cost capital to allow them to put the project in. So if you can go to the next one. So commercial CHP. Commercial is really tough for turbines because commercial is typically smaller buildings. And for a turbine, you're typically more in the, except for the microturbine, and the Capstone folks will talk about that. But in the larger industrial turbines, we're typically 3 megawatt applications and above. The top application is the Foxwoods Casino, the Massachusetts Pequot tribe in eastern Connecticut. But it has a very large facility if anybody's been there. They have 2 7 megawatt turbines there. But they have steam production. They have steam for absorption chillers in the summertime when it's hot there. So it's tri-generation, but it's for a commercial application. The bottom picture is actually a picture of it's a chilling application where the turbine exhaust goes directly to a chiller. We have a few examples of that. Data centers could be an example of that. This particular picture, though, actually has to be the Thai Government Center in Bangkok. Not a U.S. application, but they provide hot water, chilled water, and steam in a lot of these different applications. So if you go to the next. So when you look at the steam needs, there are many different applications. So this particular application is at an ethanol plant. So the city of Russell, the actual public power entity in Russell, Kansas, takes the power at cost-effective rates because the thermal is sold to an ethanol plant. The ethanol plant needs steam for the digestion, but they don't need as much power. So the heat rate chargeable power, if you credited what you would use in a boiler to make steam, is very cost-effective and even more efficient than a large combined cycle plant. So you can go to the next. But we also have what we call supplementary firing. When I mentioned before, we have quite a bit of oxygen in the exhaust. It allows you to vary the amount of thermal that you can produce. This example is actually the Tesoro refinery in Utah. They make a lot of steam because the refinery needs a lot of steam for processing. This is 2 15 megawatt units, but each boiler has the capability to go from 60,000 pounds an hour up to 240,000 pounds an hour of steam production, and almost do it within a very, very short period of time. In this case, the refinery only needs about 15 to 20 megawatts, and they sell some of the excess power to the grid, to the Utah Power grid, at rates that allow them to save significant money on a monthly basis to their utility cost. You can go to the next. So other applications for turbine exhaust, because you have a lot of high-grade quality heat, is example now is tissue drying. This is actually a ceramic dryer where they take slurries, and we do a lot of this in places like Mexico and Thailand. We don't have many tile manufacturing in the U.S., but in place of doing it for a spray dryer, we have a lot of gypsum. So if you go to the next picture, companies today, recycled energy put in for National Gypsum a 4 megawatt cogen plant where they take the heat and they dry the gypsum. Gypsum is used for, you know, wallboard production and things like that. Gypsum is a calcium sulfate dihydrate that comes out of the ground and they have to dry it and things. But those are good examples of how cogeneration using the heat can be deployed in lieu of having to use fuel for only one source of energy, drying or heat. And so that's really the purpose in that case. So if you can go to the next one. And then the other thing that people don't really think about is heat for chilling. And so steam can be used to steam turbine drive chillers. The bottom right picture was a demonstration by the DOE of absorption chillers using the turbine exhaust directly in an absorption chiller. Today, though, those applications are not as great. Data centers have changed the amount of chilling they need, so perhaps those applications are not as great. But when you look onto the bottom left, that's a York steam turbine drive chiller. So projects that we have a steam need demand in the winter time for heating, they can change and use that steam to drive steam turbine drives as opposed to using electric chillers during the summertime when power prices are higher. And one good thing about these projects also as well is when you make chilled water, the upper right picture is a thermal storage tank of chilled water. So this is Dell Hospital. That's an 8,000 ton-hour still chilled water storage tank. So what you think about that is you can use your chillers off-peak and fill that up with chilled water. And you think about today the developments that people are trying to do for batteries and other things to have peak demand. This is one of the better ways because today that's a proven technology. I'm out in San Diego. University of California, San Diego has a large thermal chilled water storage tank. TECO in Houston has the same thing. These are very available in ways of providing chilled water and reducing. If you look at 8,000 ton hours, if you think about a kilowatt per ton, so you got an 8,000 kilowatt storage tank right there. Think about what that would be in terms of batteries. So you can go to the next one. So talking about thermal is always the key. How do you use the thermal? But what also people have to realize today, natural gas is something that we have in the U.S. and are enjoying the privileges of it at a low cost. But there are many other alternative fuels that can be used. And it's best to always use those waste fuels whenever possible. So we're doing a lot of different fuels today, not so much coke oven gas. We are looking at a few coke oven gas projects in the U.S., but we have over 40 of them in China, and the EPA has actually given the first international award to Chinese companies for reducing their carbon footprint by using coke oven gas and CHP. If you go to the next one. Here's an example of a manufacturing plant. You can probably figure out it's a South Carolina German car manufacturer. They take neighboring landfill gas and provide 10 megawatts of their electric demand to serve that manufacturing plant, and they produce the steam for their needs in the manufacturing of cars, and it's all done with a renewable fuel from landfill gas. And in South Carolina, which is really a low-cost electric rate, this is a very cost-effective way for them to produce on-site power with CHP. So if you could go to the next one. This is a little bit of a different application. This is an Air Products project, but this is a project that's just now in commissioning, and we're still going through some of the early trials of this, but they're actually taking waste garbage, MSW, gasifying it into a fuel that we're burning it in our combustion turbines and making power. If you're in a district heating plant, you could use that exhaust heat instead of going to a steam turbine. You could put into a city and use district energy, and combined heat and power would be a great application in being sustainable and using your local waste from a city production. So if you could go to the next one. I mentioned that the U.S. has a good supply of natural gas. And this is a recent chart that we look at the disparity between gas prices domestically and in Europe or Japan. Think about being a manufacturer in Japan and having to compete on the world market when you're paying $16 a million BTU for gas. Where here in the U.S. the price is below probably $5 on a delivered basis. So what the U.S. has to do is be good about its resource, but do it effectively in combined heat and power, because we don't just want to be inefficient and use our natural resources so that our future generations are then in trouble because we were squanderous in how we did things during our careers. And so, but we do need to take advantage of our competitive nature with natural gas. And if you go to the next slide, what really this means is looking at the future in our spark spread. So what does it mean to be competitive with combined heat and power if you're putting it at a manufacturing plant, a brewery, or a pharmaceutical operation? It's really what's called the spark spread, the difference between the natural gas price and the electric rate. And there has to be enough disparity there. So today, and there's still a lot of low-cost states for electricity. Kentucky, as an example, is one of them, but Kentucky is still a very coal-predominant producing state. Arkansas is the same, but as you look at what's happening, these plants are having to be retired. Most of them are in the 30 to 40-year age. And as we go forward with continual greenhouse gas emission requirements, they're going to be shutting a number of these plants down, or they're going to have to restructure them with add-on costs to meet environmental regulations, the Clean Air Act, things like that. So in the future, if you look at it, gas prices are expected to stay relatively stable because of the amount of shale gas production that's available in the U.S. But the electric rates are only going to have to go up because of infrastructure demands, coal retirements, and a host of things. So if you go to the next one. So, you know, these are just examples of can you depend on the grid. Hurricane Katrina up in the upper left. The bottom right is San Diego. That's my backyard. In 2003, the fires were caused by grid lines out in the desert area. Windstorms in the Midwest are in the upper right. The lower left, if people in the Northeast remember the Halloween autumn snowstorm. So if you go to the next. So what will the grid of the future look like? You're hearing a lot about microgrids as an example. So people want to be able to integrate CHP, solar, wind, and other things, choose between the main grid or a microgrid. If you go to the next. Here's an example of a microgrid right here in my backyard. University of California, San Diego has two of our 15 megawatt combustion turbines as the anchor of their CHP. But they also have fuel cells burning digester gas. They also have solar voltaic. So they've integrated all that in and have a microgrid to allow them to best choose which options to pick in terms of their energy production. But I think CHP is probably the ideal way of anchoring any future microgrids. So we could go to the next. So really in all of this, we make a variety of different products, and you can find this on our website. I don't want to go over it all, but we make anywhere from really a megawatt up to 22 megawatts in engine generator sizes. And you can put in multiple units for reliability if that's your thing, but if you go to the next slide. And this gives you an indication of the steam production. So there's a whole variety of different steam demands, and you can get that flexibility with combustion turbines with we talked about the duct firing options. And the efficiencies are quite good. When you look at the high fired efficiency levels, those are when you get up to the 90% type applications. So if you could go to the next. So we have more than 15,000 turbines out in the world in about 95 different countries, but we support them. In the U.S., we have major overhaul facilities in Texas. Our major manufacturing is in the U.S. We're one of the major exporters out of the state of California. We're probably the third largest manufacturing exporter. But we service them, and that's one of the things that when you buy these are not while they're high tech, they're something that your existing operators can utilize, and I think they would be comfortable with just a little bit of training. So if you go to the next. So we can provide all this services, everything from A to Z. If you go to the next, wrap it up here. We think combustion turbines are a great choice, and if we can be of any help, you can go to the next slide. You can contact me. We'd be happy to support any of your CHP applications, and then I'll turn it over to the other speakers to give you the other technology options as well.
Thanks, Chris. There was one question that I wanted to ask you, but in the meantime, I'd also encourage other audience members to please go ahead and type in your questions. And the question that was asked was, do you have examples of CHP using digester gas and that also have NOx and CO control?
Yeah, that's a good question. We're actually just commissioning right now 3 Mercury 50s burning digester gas in Washington, D.C. at the wastewater treatment plant. We've had Los Angeles County wastewater treatment plant's been in operation for almost 30 years, continuously for the last 30 years. It has 3 of our 10 megawatt turbines. What they do there, though, they use water injection to reduce the NOx, because in that particular engine, the heating value is too low. It can't be burned in a dry, low emissions combustor. The Mercury 50, because it's recuperated, they can burn landfill and digester gas. We just commissioned a couple of months ago DT Energy in Los Angeles, a 20 megawatt landfill gas project without environmental controls in Los Angeles burning landfill gas. We have another project with the city of Los Angeles, which has 2 of our 10 megawatt units that are being installed now at a digester plant. In Oakland, we have a Mercury 50 burning digester gas without any back-end environmental controls, and it meets the state of California environmental regulations. So we can do that quite effectively, and we have a number of experiences doing that.
Another question that that's been asked is, how does the co-carbon gas CHP work? Aren't there a lot of pollutants in the gas?
There is, but what happens is we clean the gas, so there are a lot of tars and things and particulates, but we have cleaning technologies that remove those. There is quite a bit of sulfur as well, but there are technologies available that remove the sulfur in the fuel gas, so you don't have to do anything in the flue gas.
Gotcha. And then the final question before we turn it over to Mark is, when combusting landfill gas, how do you deal with siloxane removal, and what's the cost?
That's a good question. Siloxanes are a silica that's in everything from shampoos, deodorants, and things like that. And what happens is, it's in the gas, and when you combust it at high temperatures, it melts, and then as you cool the gas in the gas turbine, it then solidifies on the turbine blades. We used to just deal with it and just let it pass through, but we've since developed technologies just the same way you would remove moisture. When you drop the water out and cool the gas, the siloxanes come with it. And then you also have other technologies like a silica, not the silica, but the gels that dry air. They use those type of technologies in a carbon filter with some chilling of the water, of the gas, to knock the water and the siloxanes down. And that gets it to levels that allow us to operate the gas turbine.
Thank you, Chris. And Sarah, if we want to start loading Mark's slides, I'll ask Chris one last question. Can you give some examples of biomass facilities using CHP?
Well, in the U.S., we don't have any biomass gasification projects, so we are a gas turbine company, but there are a host of biomass projects in CHP that they burn the biomass in a boiler, and they make steam. They have steam for steam processes like the paper mills and things, use a lot of bark and things. So they drive a steam turbine and use steam for process. That's an example of using biomass for CHP. And that would be a boiler, just a mass type boiler operation. We're not in the boiler business, we're in the combustion turbine business. We would want to have that biomass done as gasification of biomass, which is a potential, but it's an early stage technology. I think at this point it still needs improving.
Thanks once again, Chris. And we will now turn this over to Mark Rouse at Capstone. Mark, please take it from here.
Hi, thanks everyone for attending. I'm Mark Rouse. I'm at Capstone. I'm a sales director covering the US and Canada. I'll give a little bit of an introduction to our distributor network in a later slide, but we do work through a worldwide network of distributors that can provide application support, and over half of our business is combined, nearly half of our business is combined heat and power. So we have a lot of local expertise with permitting and applying these systems to any user's need. Can I go to the next slide, please? So just a quick background. Capstone's been around for quite a while. We were founded in '88 and went commercial in '98. We're publicly traded and the world leader in microturbines, which we now define as a single microturbine under about a megawatt. Everyone seems to be getting bigger, and so are we. I'll show you more of our lineup in a later slide. We are headquartered in California, and we do all of our manufacturing in the Los Angeles area. And we cover the world through service and sales support through a network of about 95 distribution partners that have exclusive territories. To date, we've shipped about 9,000 units, and we have about 60 million operating hours, so it's a proven technology at this point. Next, please. So what is CHP? Some of this is going to be a little bit redundant after Chris's presentation, but I think I have a little bit different approach here. So, two outputs, like Chris said, we produce power and we beneficially utilize our waste heat to produce heating or cooling are two of the most typical uses. We locate the CHP near the point of use for the heat, which is a key to how this works. Some of the normal functions we use for the waste heat is space heating with low pressure steam in our case, or hot water, space cooling with an absorber being used to make cold water, dehumidification processes, and then we can also do direct heat usage with our low emission systems for cooking or sterilizing or powder coat type applications. Drying processes as well. Next, please. So this is kind of the whole heart of why CHP works, why it is green, why it does actually save money compared to business as normal. So on the left side, I have an illustration of a Capstone system with combined heat and power. And on the right-hand side, we have businesses as usual with purchasing power from a local utility and running a boiler to produce hot water or heat, space heating, whatever you want to do with the heat. In both of these examples, we have the same outputs, the same two outputs. In this case, 120 kilowatts of hot water and 65 kilowatts of electricity. You can see that in the blue on the bottom. Both of those are equal. In the case on the right-hand side, we have emissions being produced from the local utility, which is generating somewhere down the line, and also emissions from your boiler that's running natural gas. Because of the relative efficiencies and the delivered power efficiency from the grid at about 33%, we see the amount of fuel required by these two sources. So the utility is burning about 195 kilowatts of fuel to deliver 65 kilowatts of electricity, and your boiler is burning about 150 kilowatts of fuel to produce the 120 kilowatts of hot water output. In the case at the left, we're using one source of fuel to provide both the electric output and the heat. So you can see with the same two outputs, we're only consuming 230 kilowatts of fuel. So we're using significantly less fuel because we have a higher overall efficiency than the combination of purchased utility power and a boiler. So that reduction in fuel is what allows emissions to be much lower, in addition to the lean, low NOx, low emissions gas turbine system providing lower emissions than the typical utility, running natural gas or coal or whatever the mix is, even in California. So this is where the economics come out. Less fuel is less money, and also where the emission savings and the green aspect actually comes from. Next, please. So typical CHP paybacks, I included this slide because a lot of people are looking at spark spread and wondering if they are a candidate for CHP. In Chris's presentation, he mentioned the spark spread, which drives the economic return on projects, and I wanted to give a few examples of states with different average commercial electric rates and what we can achieve payback-wise with the CHP system. So the purpose of this slide is to show that you really don't need to be paying a lot for power to get a reasonable payback when you're doing CHP, provided that you're sizing the system appropriately to the heat load. So we can see with rates as low as 8 or 9 cents, you can get an attractive payback, and there are federal and state incentives available that vary wildly, but our distributors can help and show you what's available. You certainly see states like California have the best paybacks with high electric rates, low gas prices, and a very generous incentive program. Same goes for New York State. But we can get it to work in most states with today's spark spreads. Next slide, please. So why microturbines? Microturbines should be used for CHP because of the wide range of sizes we cover, how we can cover and precisely size and fit your heat needs, even in smaller applications like small hospitals or schools, and the very low maintenance and low emissions aspects of the system. Basically, it does allow us to bring all the benefits of a large gas turbine to applications that typically would not be able to house a system or utilize the outputs. Next, please. This is an example of our 65 kilowatt machine. It's about 3 feet wide and about 6 feet deep, and it's between 6 and 8 feet tall, depending on the options here. So what we see on top of the machine is actually an integrated hot water heat recovery system. It's about 40 gallons per minute with a 20-degree temperature rise. The unit on the right is actually our low emission system, which can be installed without a permit in places like California. It's CARB certified, so this is just an example of the relative size. It's really easy to shoehorn these things into a facility and to put multiples of them in. Next, please. So the environmental benefits, besides the payback, which does typically sell the project, we can show this reduction in criteria of pollutants and equivalent cars removed, fuel saved, however you want to look at it, versus business as usual. So that would be running a boiler, purchasing power from a local utility versus maximizing your CHP by getting as much heat as you can as a base load from the CHP system. So, this just shows a very big reduction in especially NOx. CO2 is reduced significantly because of the increase in efficiency and burning less fuel. You'll see that 28% is pretty close to the energy saved per year. It's just the efficiency improvement. Next, please. Chris also mentioned this, CHP can provide backup power, and unlike a backup-only generator, you already know that it's running before you have an event, and it's not just a cost. We can actually provide a return and also be there when you need resilient power in the case of an outage. Tropical Storm Sandy or Hurricane Sandy left a lot of people without power for a lot longer than their diesel supplies lasted with their recips. Using a natural gas CHP system allows you to run through events where fuel delivery may not be available. All of our sites in the Northeast did run for the entire week that it took to get power restored in some cases. So we actually got a lot of interest after that storm, and there are incentive programs set up to provide resiliency because it does add value to the community, especially in places like schools and hospitals, Red Cross, disaster relief points, and things like that. Next, please. So, why are microturbines a fit for CHP? Turbines in general have very low operating and maintenance costs. Every dollar you spend on operating and maintaining the equipment is just that much more you have to make up for in spark spread. So we bring that advantage to smaller scales. It's proven technology, but it's still, cutting edge and low emission. It's very high reliability, low total cost of ownership, low noise, no vibration, and low emissions. So it's very easy to live with, even in settings like hotels. Next, please. This is just a quick case study. Since this is a financial ROI sale, I like to actually talk numbers. This is in California, so it's probably a little bit better than what you'd see in other parts of the country, but we can certainly take a look and show that electric rates don't have to be that high for these systems to work if they're sized appropriately. But this is up in Northern California. It's a medical center. It has 12 of our 65 kilowatt machines. So we generate 750 kilowatts of power. It's been running now for about 5 or 6 years, and we base load the building. So we provide almost all their base load, 750 kilowatts. Their base load's about a megawatt, and then almost all the heat that their boiler uses base load. So the benefits are NOx reduction, 72 tons a year, CO2 reduction of 1,700 tons per year. And all that with a payback of 2.5 years, which includes the self-generation incentive program in California. But this system is actually saving the hospital $450,000 a year in utility costs, all while reducing their carbon footprint. Next, please. So I'll just leave you with some contact info and how you can hook up with the local distributor. I can always put you in touch with the local distributors if you tell me where your project is. My email address is mrouse@capstoneturbine.com. And thank you for attending today.
Thanks, Mark. I just thought, while we're waiting for some more questions to come in, I wanted to ask you 2 questions, please. First of all, can you kind of talk a little bit about sizing systems so that, we normally in the CHP world talk about sizing to thermal as it ties back to even efficiency. Do you think you could elaborate a little bit on that?
Yeah, so because you're dealing with 2 outputs with a CHP system, some thermal output and electrical output, you need to keep both in mind when you size. In most systems, to optimize a payback, you want to run the equipment 24/7 so you get as much production as possible. So what we would look at is your base electric and your base heat or cooling load so that we can run our system at full power 24/7 and utilize both of the outputs completely. What we'll do is we'll take the lesser of the base load, if it's heat or electric, and then size the system based on that.
And the other question I had is, at what power price does the technology work best?
The power price depends on tax appetite for end users, their ability to take advantage of different incentives and programs that are offered on the federal and the state level. And it also depends on natural gas prices for natural gas powered CHP. In today's market, with today's gas prices, we can make a system provide a reasonable payback with power as little as 8 cents. But having said that, we have seen customers that have much higher tolerance for longer paybacks and want a system for the green aspects, and we've seen some customers that want incredibly high returns on equipment that just aren't possible. So really we can't pinpoint an exact number where the system works or doesn't work, but if we know the natural gas price, the average electric price, and the customer's tolerance for a payback, we can estimate what the payback would be.
The one question that that's come up regarding microturbines is that, can you give a cost estimate if someone decides to install a microturbine for CHP?
Yes, so the issue with pricing a CHP install is that the microturbine part of the project is only a small part of the overall cost. So the CHP system is going to consist of the microturbine cost and the installation cost and some third-party equipment for utilization of the waste heat. In general, the microturbines cost around $1,000 to $1,200 per kilowatt, depending on the size and the features. So we're very competitively priced with quality recips and with larger gas turbine systems, especially low emissions systems for our equipment. Typically, by the time you get to a recip or a microturbine powered CHP system, you're going to be looking at $2,500 per kilowatt for most systems with a basic hot water or low pressure steam installation.
Can you discuss utility standby rates and tariffs and how that affects feasibility?
You know, it can have a significant impact on project payback. When we model a project, we do take all those factors into account. Typically, the bulk of your savings is going to come from reduced kilowatt hour purchase and reduced demand charges over time. Because of the modularity of our system, demand charges are pretty easy to get away from because any maintenance event only takes out part of your array if you have 12 C65s or 5 of the 200 kilowatt machines. So we can actually get away from demand charges in a way that some other technologies may have a harder time. Standby charges and departing load are things that I would like to see go away. You know, for people that aren't familiar with it, if you put a megawatt of new generation at your facility, some utilities, not all, will charge you for a megawatt of departing load. So there's some fee they'll have for, you know, having once provided you essentially with that megawatt. Generally speaking, in places where we see those sorts of tariffs, it does not ruin the economics. It just will add, you know, maybe half a year to the payback. And we're working actively to try and get some tariffs out there that make a little bit more sense in that respect.
Thanks, Mark. I guess on this question, I also wanted to see if Tony or Chris have any comments.
Yeah, I just figured out how to unmute myself. I would have a sort of a similar response to that in terms of we also, because so many of our projects are customer side of the meter, would like to see things like standby charges and departing load charges go. They do impair the economics a little bit, so you have to work around them.
Chris, do you have anything to add?
Yeah, this is Chris. I agree. I mean, but you have to realize if you want standby power from the utility, you have to pay for it. So you can't have it for free. It does affect the economics, but what has to be done is it has to be looked at more economically as opposed when it's needed, you should pay for it, but not have to pay for it if you never need it. So just leave it at that.
Thank you. Thank you, Mark. I think at this time we'll turn it over to Tony.
Okay, hello everybody. My name is Tony Leo. I work for Fuel Cell Energy. I'm the Vice President of Applications and Advanced Technology there, and I'll be talking about the application side of things, in particular combined heat and power. If we could have the next slide, please. A little bit about Fuel Cell Energy. We manufacture a line of power plants based on molten carbonate fuel cell technology. And that's a commercial product line we have. We're also doing research projects on other types of fuel cells and other applications of carbonate. But our bread and butter are mostly combined heat and power systems based on this carbonate fuel cell system. We're based in Connecticut. We have a manufacturing facility and offices in Connecticut. We have a manufacturing facility in just outside of Munich in Germany as well. And our Asian distribution partner, POSCO, has a manufacturing facility in South Korea. And we have units and service people all over the world, more than 50 sites, 9 countries, more than 300 megawatts either running or being installed. Next slide, please. So why are people interested in fuel cells? What's so good about fuel cells? And that first bullet there is pretty much the whole story. It's the production of power without combustion. And you're essentially converting a fuel to electricity the way you convert nickel and cadmium to electricity in a battery, or lead and acid in a battery. Instead of a flame that makes a hot pressurized gas that spins a machine that spins another machine, you are directly converting the fuel to electricity by reacting it in a fuel electrode and an air electrode with some kind of electrolyte salt bridge between them, and fuel cells tend to be characterized by what that electrolyte is. They are all characterized by this very low emissions as a result of a lack of combustion. Few moving parts, because your prime mover is basically a stack of electrochemical plate reactors. They started out, of course, in the space program, but they're now available at distributed generation sizes commercially for operation on natural gas, biogas, and a variety of other fuels. The vast majority of them are deployed as in CHP applications where the waste heat is utilized. In particular, the type of fuel cell that we make, high temperature fuel cells, are really good for combined heat and power applications. The other aspect of it is our output is direct current power. It is converted to alternating current power with inverter systems, not unlike what are used on solar systems. So those inverter systems have some benefits associated with reactive power capabilities and different tricks you can do when you're running an inverter. The next slide talks a little bit about the specific chemistry of the carbonate fuel cell. So it's considered a high temperature fuel cell. It runs at about 1,000 degrees Fahrenheit. And one of the things you have to do with fuel cells if you want to run them on natural gas or biogas is you have to convert that hydrocarbon fuel to hydrogen, because that's what the fuel cell wants to consume. And for lower temperature fuel cells, that's done with a separate reforming system. And in some cases, like vehicular fuel cells, that's done completely off board and you're running on pure hydrogen. What's interesting about high temperature fuel cells like molten carbonate is you can do that reforming reaction inside the fuel cell stack. You can send methane and steam into the fuel cell stack and it will be converted to hydrogen there. And what's really good about that is that that reforming reaction requires heat, and instead of burning fuel to provide that heat, you're providing the heat through the waste heat of the fuel cell. So it's a very efficient way to make hydrogen. So we convert the hydrocarbon fuel to hydrogen right inside the stack, which is where we consume the hydrogen in that anode reaction. That produces electrons, which go all the way back to the cathode, which consumes electrons and also consumes air. So fuel goes into one side of the cell, air goes into the other side of the cell. There's a little CO2 cycle in there that's associated with the fact that our ion transfer electrolyte is based on carbonate ions. Next slide, please. This is what a single fuel cell looks like. The working part of a fuel cell is a thin sandwich of the anode is a porous nickel material. The cathode is another porous nickel material. In between them is a porous ceramic that we call the matrix, and that is essentially like a ceramic filter paper. And our electrolyte, which are lithium and sodium and potassium carbonates, our electrolyte is wicked into that matrix material. So that thin anode matrix cathode sandwich is the basic working part of the fuel cell. On either side of it, we put simply corrugated stainless steel that provides the gas channels, and we flow that fuel gas, that methane steam mixture is flown over the anodes, and hot air is flown over the cathodes. Next slide, please. And this gives you an idea of physically what these things look like. The fellow in the picture on the left is holding a single fuel cell. So you saw that cartoon on the previous slide. That's what a real one looks like. It's a little bit more than 2 feet by 4 feet, and it makes just under a kilowatt of power. And what's directly behind him is a fuel cell stack. It's 400 of those individual fuel cells, which after DC to AC conversion and accounting for parasitic losses will net 350 kilowatts per stack out to the grid. The picture just to the right of that shows that we configure 4 of those stacks with manifolds in a 4-stack module that will net 1.4 megawatts. And then when you go further to the right, you'll see one of those 4-stack modules is used in our 1.4 megawatt system. 2 of those 4-stack modules are used in our 2.8 megawatt system, and that's the biggest system we make. Customers do larger projects, but they do them with multiples of that 2.8 megawatt DFC 3000 system. Next slide, please. So besides the fuel cell stacks, this is what else goes into a fuel cell power plant. So we have fuel treatment and water treatment. And fuel treatment is basically to strip out things like sulfur, that would be put into natural gas as odorants or to strip out sulfur and water and siloxanes that might be in biogas. We do send a mixture of steam and fuel into the fuel cells to support that reforming process, so we have a little water treatment system on board as well to make sure that water is clean enough in terms of dissolved solids to be evaporated and sent to the fuel cell. So that fuel steam mixture goes to the fuel cell anodes. All the fuel is converted to hydrogen. About 70% of the hydrogen is used to make electricity, and we leave 30% of the hydrogen left over to send to a catalytic oxidizer that helps heat up our incoming air, because we don't want to send cold air into the fuel cell stack. So we use a little bit of leftover hydrogen to heat the incoming air, so we're now sending hot air into the fuel cell cathodes, and we exit the stack and use the exhaust from the stack to provide that preheat for the fuel and water coming in. When we exit the stack, we're about 600 C, or maybe 1100 degrees Fahrenheit. After we do that fuel and water preheat, we exit our exhaust at around 700 Fahrenheit or 370 C. And that exhaust is what's used, as I'll show you in a couple slides, for a variety of different heat recovery applications. So next slide, please. So that was a cartoon of what the system is, and this is a picture of what an actual fuel cell power plant looks like. This is actually that UC San Diego system that Chris mentioned before. You can see in the back there the two 1.4 megawatt stack modules, A and B, and what the mechanical equipment running in between them is what we call the mechanical balance of plant. Directly in between them is the heat recovery system that does the preheat of the incoming fuel and water. Now, typically, another heat recovery system is added after this one to do the heat recovery. The day that we took this picture at UC San Diego, they had not yet installed that, but they've since installed absorption chiller waste heat recovery system. So moving toward the left of the picture, after that heat recovery system, the other mechanical equipment you see there is basically just startup heater, a fresh air blower, and then the water treatment system is all the way to the left there. On either side of that mechanical equipment directly connected to each stack module is the DC to AC power conversion systems, one for each stack module, and that AC power is connected into the grid through that switchgear that you see in the front. So that's a 2.8 megawatt working fuel cell power plant. It's about 50 feet by 60 feet in terms of the space that it takes up on the site. Next slide, please. And our units tend to be deployed into these two types of applications. One, which is more typical, say, in California, is on-site power. That's where a customer puts a unit at their facility and essentially reduces the amount of power that he consumes from the electricity. And these are almost always combined heat and power. So he makes power for himself, so he has to buy less from the utility, and he makes heats for himself so that he has to burn less fuel, saves money, saves emissions, and so forth. And as we'll see in a couple slides, often deployed these days to support energy security through microgrids. The other type of application is electric grid support. These are larger systems where electricity is sold to the utility by independent power producers. You would think that these would be less likely to be combined heat and power, and that's true, although it's quite surprising how some very large systems, particularly in areas where there are district heating systems, are deployed even for these large grid support applications in combined heat and power. Next slide shows a little bit about what makes fuel cells so attractive, and that's these two things, high efficiency and low emissions, both of which stem from that electrochemical conversion process that I mentioned. So this compares fuel cell emissions and efficiency to the average U.S. grid and the average U.S. fossil fuel plant, and this is the U.S. we're talking about, so you know, these numbers are dominated to some extent by coal. And so if you look at the first DFC fuel cell line, DFC stands for direct fuel cell. It's kind of the model name we give to our carbonate fuel cell, referring to that direct conversion of hydrocarbon to hydrogen. So the fuel cell itself runs at 47% electrical efficiency. and which would essentially, on typical natural gas, have a carbon footprint of 940 pounds per megawatt hour. And if you look at the NOx and SOx and PM10 numbers, they are just orders of magnitude lower than what conventional power generation produces. And that's one of the main attractive features of fuel cells. So we start out at about 940 pounds per megawatt hour. That's very low carbon footprint, but it is a little higher for some really low carbon grids that have a lot of nuclear or renewables in them. But then when you start to factor in the impact of offsetting fuel consumption in combined heat and power applications, you start to drive that carbon footprint number very low. And then if you're doing biogas applications, of course, those are carbon neutral, so you essentially drive it to zero. So low carbon footprint, very low criteria pollutants is our key attractive features of these fuel cells. Next slide, please. So these are the ways that we use the waste heat in the fuel cell. Either on-site combined heat and power, where a customer is making heat for himself, and I'll get into some examples. District heating for larger systems, and the last one, which I won't talk too much about, is if we can't find a heat user, we have, in a couple projects, found ways to convert our waste heat to additional electricity. The picture on the lower left there is a 15 megawatt system in Bridgeport, Connecticut, where our waste heat is going to that system that's right in the middle of the picture, which is the organic Rankine cycle power generation system. These are typically used to make electricity from geothermal heat. In this case, our heat is producing an extra megawatt of power from this on top of the 14 megawatts that the fuel cells are making. So those are the three ways we use heat. And if we go to the next slide, it'll give some examples of how we do combined heat and power and how it affects the total efficiency of the system. So what this slide is showing is that a 2.8 megawatt power plant system running at 47% lower heating value efficiency is being delivered 5.9 megawatts worth of fuel to produce 2.8 megawatts worth of power. And as I mentioned before, our exhaust, which is where all our waste heat is, we don't have a cooling loop, our exhaust is 700 degrees Fahrenheit. And there's a wide range of things you can do with that exhaust. And there's just a few examples given in that first box that would equate to about 3.5 million BTUs per hour of heat use. You could make 345 gallons per minute of 250F hot water, or you could make 2,600 pounds per hour of 75 psig steam, or you could do 380 tons of absorption cooling. You could do any one of those things and still have an exhaust that was 350 degrees, and you could make some additional lower temperature hot water or do some other types of low-grade heat, and you can end up with near 90% total thermal efficiency if you do some of these two-step heat recovery applications. And the next slide gives an actual example of one of those. So this is a 1.2 megawatt system. It's an early version of our current 1.4 megawatt DFC 1500. This is at an industrial bakery in Connecticut, Pepperidge Farms Bakery. And this particular unit makes about a third of their electricity. They've just ordered actually another unit, so a 1.4 megawatt unit. But this first unit makes about a third of their electricity. And the first thing we do with the waste heat is we make steam. And we produce pretty much all the steam they need, so they've been able to turn off their gas-fired steam generators. So there's a big reduction in CO2 footprint right there. And then after we do that, we have some heat left over, and what we do with that heat is we do some preheat of gases that are coming from their ovens and going to their incinerators. When you bake bread on an industrial scale, that really pleasant baking smell, you're just not allowed to emit it. You have to destroy some of the organics that's in that. And so they have an incineration system, and so by preheating that gas, they can burn less fuel in the incineration system. So it's a really good high efficiency example of a two-stage heat recovery system. Next slide, please. This is an example of a biogas application. About half of our units in the state of California are running on biogas, and the vast majority of those are running at municipal wastewater treatment plants. That's a really good biogas application because the gas is produced in digesters that have been installed with the prime purpose of reducing the amount of solid waste that they have to deal with. They produce this methane gas, which is diluted with carbon dioxide as a byproduct of that digestion. And it turns out that CO2 diluent doesn't particularly bother the carbonate fuel cell at all because of the carbonate fuel cell chemistry. That CO2 is actually a reactant on one of the electrodes. So, so we can effectively utilize the biogas. You don't have to strip out all the CO2, which is often done if you want to produce gas that's pipeline quality. So you can avoid some of the cost and energy associated with stripping out that CO2. So you can send the dilute gas after stripping out things like siloxanes and sulfur. You can send the dilute gas directly to the fuel cell. This is a 2.8 megawatt system at the Inland Empire Utility Agency, and what you can see to the right there, our exhaust is being ducted to a hot water heat recovery unit, and that heat is very important. That goes back to the digesters. The digesters have to be kept at a certain temperature, a certain elevated temperature, so that the bugs that are digesting all this solid waste are happy and keep digesting. And so that's the main use for waste heat recovery at one of these wastewater treatment plants. And the alternatives, you have to do something with that gas. You can't just emit it, or you would have just a tremendous greenhouse gas impact. It's methane. So their alternatives are to flare it or to burn it in piston engines, which is often done. And when you look at the amount of NOx that's produced by those types of alternatives, a project like this saves about 10 tons per year of NOx compared to engines, and even more compared to a flare. So it's the kind of thing that the South Coast Air Quality Management District, in the case of this unit, really encourages wastewater treatment facility operators to utilize. Next slide, please. So this is the largest system in the world. This is 21 of those DFC 3000 units. And it's a 59 megawatt system just outside of Seoul, South Korea. And we were quite surprised at the fact that our distribution partner, POSCO, was able to actually make this a combined heat and power application. On top, you can see it fairly clearly on the picture on top. Directly on top of that mechanical skid is the heat recovery equipment. All the way to the left of the picture, you can see the actual heat exchanger, and you can see a bypass valve just in front of it. And that's all on a platform that's directly above there, so it doesn't add to the footprint. And that waste heat is basically going into a district heating system. So it's a really good example of how even at significant grid-connected scales, you can still find things to do with the waste heat and enjoy the carbon reduction benefits associated with combined heat and power. Next slide, please. So this is an example of a university installation. This is at Central Connecticut State University, just outside of Hartford, Connecticut. And the waste heat here is being used for heating in the winter and absorption chilling in the summer. The emissions profile supports some of the goals that this university and many other universities have for sustainability. This is also part of microgrid, which is becoming more and more common in the Northeast as a result of some of the weather events that were mentioned earlier before. And this is an example of a private investor who's taking the tax benefit in a power purchase arrangement with the university and monetizing some of the available tax benefits and making the transaction relatively transparent for the university. Next slide, please. And this is a very similar installation, actually, at a hospital. This is at Hartford Hospital. This is also a third-party PPA arrangement. In this case, the third party, the owner of the system, is the Hartford Steam Company, and they actually operate a district heating system in the area of this hospital. So the waste heat, some of it is sold to Hartford Hospital, and what they don't want to buy, they just supply into their own district heating system that they run. The electricity is all sold to the hospital, and it also is part of a microgrid. Next slide. So there's a couple examples that I was just showing of this microgrid, and it came up in some of the earlier talks. And largely as a result of long power outages that we experience in the Northeast, as well as other parts of the country, more and more interest in this. We've spent a fair amount of time building features into the system so that they are microgrid friendly. there's this protocol for the way different power systems communicate to each other when they're in an islanded off-grid situation called CERTS, CERTS. So we've made sure that our inverter systems and control systems are compatible with that. The Central Connecticut State University example I showed is one. We also have San Jose Wastewater Treatment Plant is also deploying our unit as part of a microgrid. University of Bridgeport and UC San Diego that we talked about earlier is a number of examples. And there are a few more examples. It's definitely a growing application of the system. Next slide, please. So just to wrap up, the reason why these things are being deployed in microgrids and in on-site combined heat and power applications in general is because people realize the benefits of using this type of system in the CHP application. The high electrical efficiency is particularly important, for example, to the wastewater treatment operator. He only has a certain amount of gas. So a higher efficiency system will produce more electricity for a given amount of gas. So that becomes important to them. And the high quality waste heat, the ability to make steam, if that's what you want, that's important to some of our customers as well. The fact that you can do a variety of different things with the waste heat is also very attractive, leading to these high total thermal efficiencies. And what makes it all kind of enables all of this is the fact that you can site these systems near that thermal user. You can site them at universities because of those last two things there, is that they're very, very low emission profile, which makes them both not only politically correct, but you bypass a whole lot of things like air permitting and so forth like that because of certification to CARB 2007 and stuff like that. And also the low noise. These things are just, they are good neighbors. And all that adds up to an attractive package for combined heat and power applications. Thank you.
Thank you, Tony. There's several questions, and I'm going to start off with the ones that pertain to fuel cell, and then there are a couple of questions that have come in that I think would really be helpful to get everyone's feedback. So the question that was asked is, what is the source of the hydrogen that's used in the fuel cells?
The hydrogen almost always comes from a hydrocarbon fuel. And in the case of, I'd say most of our units around the world, that's pipeline quality natural gas. You know, either natural gas as we know it in the States or LNG, which in Asia, but it's natural gas essentially. So natural gas is mostly methane with small amounts of higher hydrocarbons like ethane or propane. And as I said before, if you mix methane, CH4 with water, H2O, all the hydrogen in the water and the methane will get together to make hydrogen, and the carbon in the methane and the oxygen in the water will become CO2. And that reaction, which is called reforming, is what fuel cell people have to do to hydrocarbon fuels to convert it to hydrogen. What we're able to do, because we run at a sufficiently high temperature, is we're able to send that methane directly into the fuel cell stack and have that reforming reaction occur right where the hydrogen is produced. So there isn't really a lot of hydrogen in our system. As soon as the methane is converted to hydrogen, it's consumed at the anode. But that's where we get our hydrogen from. Typically from methane, which is the prime component of natural gas. It's also the prime energy component of typical biogases.
What's the expected lifetime of the fuel cells and the cathodes and anodes?
So the fuel cell stacks, that's a good question. The fuel cell stacks have a lifetime of 5 years right now, and we're in the late stages of finalizing the release of our next generation, which will have a 7-year life, and we're also working on longer than that, 10-year life. But right now it's 5 years, and the way that works is that after 5 years of operation, our service people will go to the site with a whole new stack module, and we'll swap out the old module for the new stack module, and we take the old module back to a refurbishment facility, and we reuse a lot of it, the manifolds and the enclosure, but we put all brand new cells in there, and that then becomes a refurbished stack module that can be used for another customer's stack replacement.
And then there are several questions on the costs of installing dollar per kilowatt. and recognition that it would vary based on location and application.
Yeah, and it does. And for the 2.8 megawatt system, for example, the installed cost, and it varies depending on what are local construction costs and how close are you in terms of proximity to the gas line and the power line. But $4,000 a kilowatt is a typical installed cost for the megawatt scale system. And we
go ahead.
I was just going to say that if you look at that installed cost and amortize that over a typical period of time and look at fuel cost and service costs, before you talk about any kind of incentives, federal or local, one of our fuel cell power plants typically makes electricity for about 12 cents a kilowatt hour. Now 12 cents a kilowatt hour is starting to be competitive at the retail level in some parts of the country. But in most parts of the country, we do need incentives like the federal investment tax credit or the California has a capital rebate program, the self-generation incentive program, and there are various renewable energy credits that are available. Those typically bring us from that 12 cents down to whatever the economic hurdle needs to be in that area.
There was a question specifically on one of the applications you showed, the Empire fuel cell. And the question is, what is the ROI on it?
I wouldn't want to speak to the customer's return on investment kind of without his permission.
Absolutely, sure.
But typically for these California on-site projects, it's getting to be a little different now because a lot of them are financed. But for a typical project where the customer is actually purchasing the unit, they really look for relatively short-term paybacks on the order of 5 to 10 years. A municipality might be willing to wait 10 years, but a typical private customer would like to see 5 years.
And there's a question about overhaul. What is the price per cost of the overhaul?
The overhaul, I think you mean stack replacement?
I am not quite sure what it means. It just says the price or cost of the overhaul.
So if you look at the cost of service of our unit, it ranges from
that is what it is, yeah.
Yeah, it ranges from 3 to 4 cents a kilowatt hour, again, depending on location. And maybe half of that is the cost of that restack.
Okay. And then there's this one question that came up that I think it would really be helpful to get everyone's feedback, and it was pertaining to PURPA, where it says, PURPA clearly benefits waste heat to power industrial facilities that can sell electricity back to the grid. The typical CHP systems that are used by universities and hospitals selling to the power to the grid, how does PURPA affect these kind of systems? And I know you all have different kind of systems for universities and hospitals, and I'm thinking you're not running much into PURPA, but just if each of you could give your feedback, that would be great.
Yeah, we do occasionally run into it. We don't run into it for every project, but occasionally we do run into it, and it involves, in terms of, from our perspective as the equipment provider, it involves supporting the customer in some paperwork associated with documenting what the total thermal efficiency is and the heat utilization, and that's all relatively straightforward. And it really depends on where the project is being done, and if the project is utilizing a specific kind of incentive, that incentive might require PURPA qualification.
Do either Chris or Mark have any comments?
Yeah, this is Mark with Capstone. Our systems are pretty easy to scale to a customer specific need. So in our cases, it's pretty rare to find a case where there's a need to export power. Most of our customers do have much higher electrical needs than they do have heat needs. That's typically the case in certainly hospitals, hotels, and most university applications. So we haven't really seen much need there.
Chris, do you have anything to add?
If it's about exporting, that is tough. I mean, if you have the thermal, you have a very cost-effective heat rate chargeable to power. But in California, as a resident, I pay 30 cents a kilowatt hour, but the off-peak rates for power sometimes is 2 cents in the wholesale market. So it's tough, even with low heat rates. And so I don't know if, Nirika, the question was on exporting power, or
it pretty much just that it talked about the mandatory purchase obligation under PURPA, and it said our typical CHP systems used by universities and hospitals selling any power to the grid, and in many cases I would think they would be purchasing if they're sized to thermal, but it depends on the application too, I would think.
Yeah.
And how does it affect your kind of system? Yeah. More broad.
I do know they tried to change the PURPA laws here just recently, but people are trying to stop that too, so that won't discourage CHP deployment. In California, they still give favorable feed-in tariff rates for combined heat and power, but the utilities are, they have to manage their costs, so they try to do as much as they can. Our company made the most money one time when we sold the CHP plant to get out of our PURPA contract with a utility in the Northeast. That year we made more money just for the future value of the contract.
And Tony, there's one question on fuel cell technologies and price. Saying price has always been an issue for fuel cell technologies. What is your company doing to drive down the cost?
A few different things. The one thing that we've been really active at over the past 15 years or so is just value engineering. We sold our first commercial unit in 2003, and its price was much lower than this, but its cost was close to $20,000 a kilowatt, and so it's essentially just year after year driving cost out of the product through engineering improvements and lessons learned. That was one key thing. Obviously, at this state, we're doing less and less of that. It's a diminishing return situation, but we still think that there is some additional value engineering room, and we continue to work on that. So that's one thing. The other thing is volume, which is essentially as we sell more, and we have fixed costs for manufacturing and so forth, that also tends to drive down the cost. And the third thing, which is pretty important, is scale. I didn't mention it, but we have a smaller product, which is a 300 kilowatt product, and its cost per kilowatt is more than twice of the cost that I mentioned for the megawatt scale. The fuel cell itself obviously scales very directly because you're just adding more and more fuel cells, but things like the mechanical equipment, the electrical equipment, even things like the manifolds and stack modules, they really go down in cost on a per output basis as you make bigger and bigger systems. So that's the other main thing that we've done as we've transitioned our market from smaller systems to these larger 1.4 and 2.8 megawatt systems. That's probably been a very significant driver in reducing the cost.
And the final question was regarding the other waste heat to power system that you talked about, application, the organic Rankine cycle. What is the average cost per kilowatt to add an organic Rankine cycle?
That also, I would imagine, is very much dependent on scale. And I'm not exactly sure, what our customer paid for Dominion Resources paid for that ORC there, but I think that they are in the neighborhood of $2,000 or $3,000 a kilowatt, but very dependent on scale.
Gotcha. Thank you so much, Tony, and we'll now turn it over to Ann, who will give an overview.
This is Mark at Capstone. We actually do offer an organic Rankine cycle 125 kilowatt system. And I think Tony's right on the cost for the generator portion. The issue I see with the ORC generators is the cost of the balance of plant. It needs a cooling tower in most cases and several heat exchangers. So the cost per kilowatt ends up it's probably coming out close to $4,000 a kilowatt installed. So I only really see it work well when you're offsetting a very high cost fuel, like maybe a diesel fuel in a gen set.
Okay. Thank you, Mark. Anne, are you ready?
Yep. So pretty much I just have a few slides here to go through, and it's really just to bring everything together for what you've heard about the different technology types, and to think about which type can be and have the best attributes for individual applications and facilities. Next slide. So this slide provides a table at the bottom that shows the different types of CHP prime movers along the top, and then some different attributes about them. And so, one of the main things about CHP is that it can be, it uses a bunch of different technology types, in order to provide both the electric and the thermal outputs that it provides. And so in the CHP catalog of technologies, 5 different system types are covered: the reciprocating engines, steam turbines, gas turbines, microturbines, and fuel cells. And so we heard about 3 of those today, but we didn't want to forget about the reciprocating engines and steam turbine systems. And you can see that they all have different attributes in terms of their electric efficiencies and their overall CHP efficiencies, which would incorporate the thermal output that is used. And so what is the overall fuel efficiency from the fuel that's burned in the system to the energy output is all incorporated in that overall CHP efficiency. There are also a variety of ranges of installed costs, as well as operations and maintenance costs. And other things that are kind of variable. We really find that most CHP systems have very high availability, but they do have minor changes between the technology types, as well as the startup time. And so depending on the actual needs of a given facility, different technologies might rise to the top as being more better conducive to providing certain electric and thermal loads, depending on what the needs for that application are. Next slide. So this is just a slide and gives you the URL for the catalog of technologies. And so there is, if you go to that website, you can download the entire catalog, or you can click on the individual chapters that will take you into the 5 technology chapters I just mentioned. And so really the catalog for each of those goes over some more detailed information about what application types, the specific technology description. So it really gets into how the technology is set up and how it operates, and a lot of the details there that we didn't have as much time to go over today. It also provides several tables of cost and performance characteristics at different sizes. And so a couple of the presenters talked about the differences that occur because of scale. And so that's one of the things that the catalog provides. So at the smaller size ranges, what are the typical costs there, versus as the technology gets larger, typically the costs go down on a per kilowatt basis. And so the tables provide aspects that you can look at one technology over the whole range of its output. They also provide information on the emissions and controls that are available to control emissions, and then as well a short section on what some future developments and research and development that's going on for each of these technologies to make them more efficient and lower cost. Next slide. So this is a chart that shows the difference in terms of the typical size ranges for the different technology types. You can see that the top, or the highest 2 technologies, the gas turbines and steam turbines, really can have, if you're looking at the larger size range, they would really be where you would probably be looking at. And just as a quick note, that the scale is on kind of a logarithmic scale. So it goes from very small units up to pretty large in the hundreds of megawatts. And so if you're looking at larger systems, those tend to be the system types you might want to go with, whereas in the medium size range and moving into some of the smaller size ranges, you get the reciprocating engines as well as fuel cells and microturbines. So it's good to have an idea of the size ranges for each of the technology types so that you're not trying to look up all of them. If you really have a smaller load, you could focus on just those smaller system types. Next slide. So there's also a difference in terms of the emissions profiles that are generated through each of the CHP technology types. Granted, CHP, because of its higher efficiency and producing 2 outputs instead of just one, like traditional electricity generation, its efficiency leads to emissions reductions. But really, when we're looking at the emissions from each of the technologies, the main factor that contributes to that is the fuel type that's used. So we really see natural gas having, one of the lowest emissions profiles, much lower than oil or coal. But you could also use CHP burning biogas or biomass that could be considered a renewable fuel, and therefore, not having the same amount of emissions associated with it. So really, the fuel type is one of the key attributes. And so we really see that fuel cells have, one of the lowest emissions impacts, which we heard talked about, and mainly because it's actually not using combustion for that electricity generation, and so it has a different type of process. But there are emissions control technologies that are available for all of the technology types. So, if there are regions of the country where, there are stricter emissions limits, those limits can really be met with additional controls on CHP systems. Next slide. So this slide demonstrates another attribute that CHP, or another benefit of CHP, is that it can provide a reduction in overall water consumption compared to traditional central station electricity generation. A lot of large central station plants use a fair amount of water for cooling, and they, can be. That's why we usually see a lot of plants, located on rivers or near lakes, or have the big cooling towers, and so they use a lot of water throughput. Whereas the majority of CHP systems would not actually use water, and that can be a real attribute, especially in areas of the Southwest where the CHP, or where they have droughts, and where CHP can provide generation without having to use that water. The steam turbine systems could be using water, but one of the attributes about CHP specifically is that water that's used to cool the system. Usually that's where the heat output comes from, and so CHP is designed naturally to take advantage of that heat. And so even where there are systems that are using water, usually that can be put into processed steam that is then used in the facility, and that water would have been needed to be generated by an independent boiler or some other thermal equipment, and so it would kind of be used anyway. So CHP really is a water neutral technology, which is pretty needed in recent years. So you can flip to the next slide, but that's kind of a sum up and bringing together of the technology types. I know we're getting to be a little bit at the end and over time, so I don't know, Niharika, if we want to have any further questions.
No, I think, thanks a lot, Anne. Now, I think this is very helpful for folks to know about the catalog of technology, and also kind of for the highlights that you provided on it. I think, Sarah, I just wanted to see if you could put up that slide that shows additional contacts and additional resources that you can use. I think it was really hard in one webinar to kind of show all the different applications. So, CHP is being used for other commercial applications like multifamily buildings that we couldn't get into, and other types of CHP systems like the packet systems that NYSERDA has kind of done a great job of getting the word out on. But we are running a few minutes over time and don't want to take up people's time anymore. But thank you so much for attending the webinar. Please do get in touch with us or our counterparts at DOE for any additional questions you have.